Imagine you've been invited to a dance party, and you're excited to show off your moves with your best friends. But wait, what kind of dance party is it? Should you be ready to do some line dancing? Is it more of a disco situation? Or should you practice your waltzing? The type of dance you'll be expected to do changes the vibe of the party. In the world of chemistry, the same is true for what kind of chemical reactions substances undergo. Sometimes it isn't enough to say a dance party or a chemical reaction to fully describe what's happening. We need more details. The different types of chemical reactions are what we're exploring in today's episode of Study Hall Chemistry, presented by Arizona State University and Crash Course. I'm Will Komar. Let's dive in. Last time, we covered the basics of chemical reactions, including how they're represented on paper. We have reactants on one side, followed by a reaction arrow, and the resulting products on the other side. At this point, we can add on to the structure by introducing states of matter, which describe the forms a substance can take. This can be a solid, liquid, gas, or an aqueous solution, which is when something is dissolved in water. States of matter clarify what properties the substance has before and after the reaction. Knowing whether we're starting with two liquids or a solid dissolved in water to form a solution, for example, can help us predict what kind of outcome we'll have. With that in mind, let's dig into the different types of chemical reactions. First, we have a combination reaction, or synthesis reaction, the merging of two or more substances to create one product. It often takes the format of A plus B becomes AB. One example of this would be magnesium combined with oxygen to generate magnesium oxide, which emits a very bright light. If we take this layout and reverse it, we get a decomposition reaction, the separation of a combined substance into multiple products. It has the overall structure of AB becomes A plus B. Decomposition reactions often require a lot more energy than a synthesis reaction, just like how it's harder to unmake a peanut butter and jelly sandwich once you've made it. Taking things apart can be messy. For this reason, we might need a catalyst, a substance that facilitates or jumpstarts a reaction. Catalysts aren't used up in the reaction though. They're just helping out. They're like a ladder that helps the reactants get to where they're going. For example, hydrogen peroxide is a great cleaner for contact lenses, but needs to be neutralized first since it can harm our eyes. Luckily, hydrogen peroxide can break down to form water and oxygen through, you guessed it, a decomposition reaction. By itself, this reaction would take a long time though, so we can use a metal-coated disc as a catalyst. That kicks the reaction into overdrive, resulting in clean contacts in a neutralized solution that's way safer for our eyes than hydrogen peroxide alone. We can see the metal disc in the reaction arrow since it boosts the reaction. Here, the reactants swap partners. We can think of the single displacement reaction as a love triangle. In the process, one of the reactants loses their partner, while the other has gained one in the form of AB plus C becomes A plus BC. Anyway, a single displacement reaction occurs when thermite, a powder used for welding, gets heated up. During the reaction, iron oxide and aluminum become iron and aluminum oxide. Likewise, a double displacement reaction follows the same patterns with two substances. Much like the swapping of dance partners, it takes the form AB plus CD becomes AC plus BD. In the reaction between lead-2 nitrate and potassium iodide, both reactants perform a switch with the substance that they're bonded to. Displacement most frequently happens between ionic substances, so the swap happens between their cations and anions. If ions are a little murky in your memory, and you could use a refresher, we define an ionic compound as a substance whose components, called ions, have positive or negative charges. For example, take the ionic compound sodium chloride or table salt. The bonds between the atoms in this compound, rather than sharing electrons, form by transferring electrons. One atom, often a metal, loses an electron, and the other, often a nonmetal, gains one. So they become electrically charged ions. Cations are ions with positive charges in the reaction, while anions are ions with negative charges. The positives and negatives attract each other, bringing those ions together into an ionic compound, like sodium chloride here. Sodium's lost an electron, so it's a cation, while chlorine gained an electron, and it's our anion. So not only are the reactants swapping substances in replacement reactions, they're also swapping charges. In the thermite example above, it's the oxide anion with a -2 charge that swaps position. In some situations, we might classify a reaction not by how its components interact, but by the products it forms. A gas-evolving reaction, which can produce a gas or a liquid and a gas, is one such case. If I take this Alka-Seltzer tablet and place it in my glass of water, it it will bubble and fizz as the bicarbonate and citric acid react in the water and produce carbon dioxide gas. Precipitation reactions are also defined by their products, this time when one's a solid. Precipitates are made when one of the substances in the reaction is insoluble, meaning it cannot be dissolved in solution. During the reaction, the insoluble substance separates out into its solid form. If this is hard to keep track of, remember, if you're not part of the solution, you're part of the precipitate. We might see a precipitation reaction in household pipes. If the water is high in metallic cations like calcium or magnesium, they can build up in the pipes because they precipitate easily at high temperatures. As you might have noticed already, sometimes reactions can fall into more than one category. We might see a precipitation reaction that is also a double displacement. Much like how some ballet moves might get incorporated into a hip-hop dance, we'll see some overlap between the reaction types we're discussing. One of the reaction types that shares some overlap with synthesis reactions is redox. To find out more, let's get on test tube. Let's take a moment to revisit the dance party you were invited to. Imagine you're taking a partner with you and you have an agreement that you'll dance together the whole evening. You're a package deal. Oxidation reduction reactions, or redox reactions, work in a similar way. You'll never see just a reduction or just an oxidation. They always occur together. Reduction is the gaining of an electron. An atom or molecule receives something negative, like if your dance partner overheard unfounded criticism of their excellent party outfit. Oxidation is the opposite, the loss of an electron. An atom or molecule loses something negative, like if you were to let go of all inhibitions and dance like no one was watching. When put together, redox is a relationship. The gain of one electron must come from the loss of that electron from somewhere else in the reaction. In the same way you might compensate for your partner's decrease in self-esteem with your increased confidence, reduction and oxidation are dance partners in perfect counterbalance. Examples of redox reactions are photosynthesis, cellular respiration, and combustion. And actually, the combustion reaction shown here is also a synthesis reaction. It's the same magnesium and oxygen reaction we talked about earlier. The crux of what's happening in all these reactions is the same transfer of electrons between substances. So whether you and your dance partner go to this party or another one, you'll still share the same transfer and balance of enthusiasm anytime you're paired up. A quick note, it may seem like redox reactions can also be double displacement reactions, but this is one place where that overlap is not the case. Double displacement reactions involve charged compounds but don't experience the gain or loss of electrons the way redox reactions do. Single replacement reactions, like the one with our friend thermite, can be redox reactions though. This process can be intense and complicated. While we'd love to go even deeper into it and the ways it does and doesn't overlap with other reactions, we don't have the time here. Let's instead move on to discuss combustion reactions. These reactions typically involve hydrocarbons, which, as the name suggests, are molecules made up of hydrogen and carbon. During combustion, a hydrocarbon reacts with oxygen in the air in a high-energy reaction to create carbon dioxide and water as its products. Combustion is exothermic, meaning it gives off heat during the reaction. As a result, we often see burning or even explosions in these types of reactions. They're the kind everyone wishes they could create during science class, but please don't. Outside of the lab, combustion reactions also play a huge part in contributing to global warming. Large-scale combustion reactions with fuel sources like natural gas and petroleum emit excess carbon dioxide gas into the atmosphere. This excess gas adds to the greenhouse effect and climate change, with lasting repercussions that affect the world unevenly. While I can't get into a rant about ending climate change here, we can identify where combustion and chemistry fits into this complex issue. And we'll continue to cover some of the impacts of human-centered or anthropocentric chemistry throughout this course, since it's a relevant and critical part of understanding science and ourselves. For now, the last reaction type we'll go over is the acid-base reaction. We define an acid as a substance capable of donating a proton and a base as one capable of accepting a proton. What this really means is that acids donate their positive charge in reactions, and bases receive positive charges. We can think of strong acids and bases as two ends of a spectrum, with neutrality in the middle. When acids and bases react with each other, they produce water and a salt. Some examples you might see often feature hydrochloric acid, or HCl, reacting with bases in the form of a metal hydroxide. To test out what we've learned so far, we can examine an acid-base reaction to see if it fits the bill for any other chemical reaction types we've already discussed. Let's try combining a strong acid and a strong base in the form of hydrochloric acid and sodium hydroxide. If we look at the ions in the reaction more closely, the two substances end up swapping partners on the product side. Which reaction type deals with switching partners? Here we go. It's double displacement. Now that we know these two reaction types, we have a better expectation for what's going to happen when we mix the acid and base together. First, swap partners, and second, the formation of water and salt in solution. This won't be the last we see of acids and bases. We'll discuss weak forms of this reaction type as well as buffers later on in the series. And that's the reaction types. It might seem like we've gone through a lot of information at once, and if that's the case, feel free to come back to this video as often as you need to so you can digest it all at your own pace. Often, the best way to truly learn chemistry, much like dance choreography, is through practice and repetition. We're covering the basics in this series, but know that there are lots of resources available if you find some of these reactions more difficult to get the hang of than others. And now that we can identify states of matter, classify chemical reactions into one or more types, and use those types to understand what happens when these reactions take place, we've got everything we need to confidently bust out our moves when we get to future topics. Next time on Study Hall Chemistry, we'll talk about the methods for balancing chemical reactions and explore alchemy as a case study. Thanks for watching Study Hall Chemistry, which is produced by Arizona State University and the Crash Course team at Complexity. If you like this video and want to keep learning with us here in Study Hall, be sure to subscribe. You can learn more about ASU in the videos produced by Crash Course in the links in the description. See you next time.